Okay. Yeah, welcome back everyone after lunch. So we'll kick off the post-lunch session on day 2. We have 2 talks in this session. The good thing about giving post-lunch talks is that if the audience stays awake, it's because the talks were great, and if the audience falls asleep, it's because the lunch was great. So we'll see how it goes. So the first talk is titled Graffiti, Secure Graph Computation Made Scalable. The talk will be given by Varsha, who is an assistant professor at IIT Tirupati. Over to you.
Thanks, Shikhar. Am I audible? Okay. I'll try my best to keep you all awake and not bore you with a lot of details and try to give you the high-level idea, which is, in my opinion, very, very simple observations that we make that allows us to have graph computations made more scalable. So I'll quickly, I don't think I have to spend too much time in convincing you guys that graphs are everywhere. So there are many real-world systems where it's convenient to model the underlying system as a graph, where you have a bunch of nodes and interaction between the entities in the system is captured via edges. And there are several interesting graph algorithms that are designed to analyze and characterize the underlying system. But the challenge that we face quite often is that these graphs could be distributedly held. What do I mean by that? Let's take an example of, let's say, a transaction network. So here I'm assuming that every node in the transaction network is a bank account, and an edge between 2 accounts captures the transaction that's been, some financial transaction that's been made across the 2 accounts. And the individual banks that hold the accounts of, let's say, all the account holders within that bank is the party that has a local view of a subgraph of this global transaction network. So, which is why I use this as an example, because if you look at the global transaction network, it could be distributed across different banks. And each bank would want to hold its data private and not leak it to the others. But then there are several interesting algorithms that the banks would like to collectively analyze the global transaction network to, let's say, identify fraudulent accounts in the network, or let's say perform credit risk analysis for each individual account, which can take into consideration the entire global network. So what would be the traditional way of doing this? Each bank would find some trusted third party to share their individual data, and the trusted third party who has the entire graph can easily perform the analysis, which is where MPC kicks in. You don't want one person who sees the entire global graph, because the person could be corrupt and may want to misuse the global graph. So what we want to do instead is run an MPC protocol that allows these banks to collectively analyze their subgraphs put together and analyze the global graph. So what we've designed is a generic framework called Graffiti that precisely allows us to do this. Specifically, what we do is when we are analyzing graph algorithms, we assume that the algorithm is represented in the form of a message passing algorithm. So I'll come to what exactly a message passing algorithm is in a short while. But just to give you a background, what is the data that we want to hold as private, as in what is our privacy concern here, is that the topology of the graph should be hidden. So each party should know only about its subgraph and should not learn anything about the edges that could be present outside its view. And scalability is another parameter that we want to account. So we might be interested in analyzing graphs that have millions of nodes and edges. So you still want to be able to analyze these graphs in an efficient manner. So just as any other MPC protocol, the parameters that we take into account when analyzing the efficiency of designing such a framework would be the rounds, the communication cost, and the computation cost. Given that this is this talk is meant for people with MPC background, I won't really get into what these parameters actually mean. Okay, so one of the first few works that looked at analyzing graph algorithms operated on the adjacency matrix representation of the underlying graph, which essentially gives you data obliviousness for free because you're operating on a matrix. If you have the entire matrix encrypted, let's say, it's easy to hide whether an edge is present or not. It's just the size of the adjacency matrix that is leaked. But this is an overkill. Okay, so most of the works that sort of operate on the adjacency matrix representation, although rounds could be, I mean, you don't really have expensive rounds because you could rely on a GC-based technique to evaluate these graph algorithms on the adjacency matrix. But then the communication and the computation cost would be very high, which is why the first work to sort of look at scaling graph algorithms was by Nayak et al. They came up with the framework called GraphSC, wherein the idea was, rather than looking at an adjacency matrix representation, they showcased how a list-based representation is sufficient, and they also gave new primitives that allowed us to efficiently analyze graph algorithms. So I'll talk about these primitives with respect to message passing algorithms also in a while. But and they also relied on a GC-based approach to evaluate the underlying graph algorithm, which means, again, they save on rounds, but then the communication and computation costs are still high. They're not, of course, they're better than operating on the adjacency matrix representation, but then you still pay the price of communication and computation because you're in the GC world now. A follow-up work was by Araki et al., where they observed that they, first of all, continue to operate on the list-based representation of the graph, which will be clear in a while. Just believe me when I say this for now. So they continue to operate on a list-based representation of the graph, but then they moved to the secret sharing based approach of designing the MPC protocol. So although they had to pay the price of rounds, they definitely had lesser communication and computation costs. And they also actually gave a round optimized protocol, which additionally saved on the rounds. But then what we asked is, can we get the best of all of this, wherein we want to have minimized number of rounds, communication, and computation, which is what this framework Graffiti is all about. Okay. Just to give you a high-level idea of the contributions, so we essentially give a generic framework for analyzing graph algorithms. And as I said, it's about establishing these algorithms as message passing algorithms, which I'll talk about in just a couple of more slides. And we don't really worry about the underlying MPC. We want the solution to be as efficient and as scalable as possible. So what we've done is our protocols are designed to have round complexity that now is independent of the graph size. So although you're operating on a list, you no longer have the size of the list being a detrimental factor. And we've, although MPC, the underlying MPC doesn't really matter, we've implemented and evaluated the protocols in a 2PC with a helper setting, just to showcase practical efficiency of the same. And as a part of the paper, we also had a shuffle protocol, which I won't be getting into in this particular talk. Okay. Just to put our solution in perspective, let's just see what exactly do I mean by a message passing algorithm. So what we essentially do is you have a graph, and each node and each edge is assumed to have some data component. So the first thing that you do is the nodes are assumed to send out messages on their outgoing edges. Of course, the generic framework of GraphSC allows you to do this over incoming edges or outgoing edges. But for simplicity, for this talk, I'll assume that each vertex is sending out messages on its outgoing edges, right? So every node sends out its data component on its outgoing edges, followed by the edges aggregate or collectively see all the messages that they have received from various nodes and update their own state. And each vertex basically looks at the information that is coming on its incoming edges and updates its own state. So this sort of a scattering of information from vertices and aggregating of the information at the vertices is performed across multiple iterations, and this is what is, or this is what qualifies as like one round of the message passing algorithm. And most of the commonly used graph algorithms can be broken down into such message passing algorithms. So we are good to go there. Some examples are BFS, PageRank, and in fact, even graph neural networks can be broken down into message passing algorithms, right? So in a secure realization of a message passing algorithm, you would want each of these components to be done in a privacy preserving manner, which means you would want the nodes to send out information privately and the messages being aggregated at the nodes also to be done privately, and the update should also happen privately. So, of course, the traditional approach of using the adjacency matrix representation still allows you to do this, but then the fact is that most real-world graphs are known to be very sparse, so adjacency matrix is then an overkill. And the cost of computing message passing algorithms when you would have an adjacency matrix would be of the order of V square, where V is the number of nodes in your underlying graph. So what did GraphSE tell us? So this was already existing. Just to place our work, I'm giving you a little background. So it essentially gave you a data oblivious representation of a graph in the form of a list. And it basically showcased how to achieve these scattering of information and gathering of information when you have a list-based representation. Right. So they proposed a data augmented list representation of the underlying graph, where essentially you have an entry for every node in the graph and you have an entry for every edge in the graph. So what would an entry for a node look like? So again, the idea is to design a data oblivious algorithm. So you want to not be able to differentiate between entries that correspond to a node and entries that correspond to an edge. So whether it is an entry for a node or an edge, you want to store similar kind of data. So every entry would have this information of source, destination, SRC which is source, DST which is the destination, and an isVertex component and a data component. So whenever you have a node entry, it would basically store the node values itself in the source and destination. And whenever you have an edge entry, it would essentially store, to capture the direction of the edge, you would have the source node being stored in SRC and the destination node being stored in DST. And the isVertex would be flagged with a 0 to denote that it's an edge, and the data component is still there, right? And secure realization of a message passing algorithm on this list-based representation, as I said earlier, is performing scatter, where information is scattered from the nodes, and then you aggregate this information over gather. And you do this across multiple iterations, which is what allows you to get a secure realization of a graph algorithm. Just to formally state things, scatter essentially allows a vertex to propagate its information across its outgoing edges, let's say, right? And the edge receives information from all, each edge basically sees the information from multiple nodes that it's connected to, and updates its data component based on, let's say, some function, let's say fs for the function for scatter. Similarly, for gather, we could have some user-defined function fg that basically captures the function that is used by the vertex to update its own state based on the information that it receives from all of its incoming edges, right? And we do this across multiple iterations. So what did GraphSE tell you? So it gave you a list-based representation, and now I'm getting into the primitives that allows you to securely realize these scatter gather operations. So GraphSE basically told us that you can order this list in a particular manner so that you can efficiently realize the scatter and gather operations. To be a little more specific, in order to perform a scatter, we arrange the list in what is known as a source ordering, wherein every vertex appears in a serial manner. So you have vertex 1 appearing before vertex 2 and before vertex 3 and so on. So, and every vertex is immediately followed by, let's say, its outgoing edges, right? So that's what I mean by source order, where the source node appears before every of its outgoing edges. And in a destination order, it's the opposite. So you have all the incoming edges that are placed before a particular vertex, right? So how would we go about performing scatter? Let's have a quick look. So you have the DAG list, which is represented by G, let's say, and you have a data component separately stored for the edge. So let's say the data part of an edge is separately stored as a list, and you have a data part associated with vertices separately stored as a list. So what we do essentially in a scatter is you perform a linear scan. You scan through the entries of the list, and essentially what you're doing is you're picking up the data component that's there at a vertex, and you're dropping those data components at edges, right? That's essentially what a scatter would do. And whenever you drop the value at edge entry, it basically looks at the function fs, which I had previously defined to compute the updated value on the edge, right? So you, this is essentially a scatter, and because the entries are ordered in a source order, it's easily doable by just performing like one scan of the entire list, right? But the drawback that GraphSC had was that although we want to store similar sort of information to ensure that you don't distinguish between entries that correspond to a node and an edge, the operations that you perform still have to differentiate between whether it's a node or an edge, right? Because you're picking up entries at a node and you're dropping entries at an edge and updating the entries only at an edge when you're performing scatter. So this requires interaction, which means there is communication that the parties the parties do communicate, and this is what we sort of try to leverage and see whether we can do this more efficiently, right? And a sequential scan would then depend on the entire list size, which is again what we try to improve. Similarly, in gather, I think this follows trivially. Just like you had scatter, because by virtue of the fact that you have the entries in the DAG list ordered by destination, you perform a linear scan. Now, unlike in the previous case, right now you pick up entries at all the edges and you drop it at a node, which is what essentially allows you to aggregate information at the vertex. Okay. If I talk about the round complexity of the original GraphSC solution, the complexity of performing scatter would be order n times rs, where I'm denoting n as the size of the list, right? And rs could be the round complexity associated with computing the function fs. Similarly, for gather, it would be n times rg, where rg is the round complexity of computing the function fg, which is predetermined. The original solution requires transitioning between this different orderings of the DAG list, which they relied on secure sort protocols, which the follow-up work by Araki et al. Observed that you don't really need to perform a sort every time, and they essentially relied on a shuffle protocol because it's the same permutation that you keep applying every time, which is the observation that they had made to improve the overall solution of GraphSC, right? What we do is we go one step ahead, and although the transitions are made efficient, we try to see whether we can improve the way in which the scatter and gather functions are computed. Let me quickly try to give the high-level idea of that. So again, recalling scatter, scatter originally is deals with not only scattering the information from a node to its outgoing edges, but you're also accounting for updating the values at an edge as a part of scatter, which is where we made this simple observation that in case you decouple the scatter, what do I mean by that? You split the scatter operations as two parts, wherein you focus on propagating the information from a vertex to edges as a separate component, and then you have a apply stage where each edge performs the computation of the function which is required to update, right? So what we essentially did, this is just formally stating the same thing, that propagate just looks at the vertex sending out the information on the edges, and apply looks at updating the edge information. Just by splitting this scatter operation into two parts allows us to achieve, break down the complexity of n times Rg as n plus Rg. And in fact, we go one step ahead and we design a new way of propagating this information, which ensures that you don't have to explicitly account for whether an entry belongs to a node or an edge, which is what allows us to actually achieve this in non-interactive manner when designing the underlying MPC protocol. And in order to actually achieve this, we had to come up with another ordering, which is known as a vertex ordering. So our solution has an additional ordering of the DAG list, which is known as vertex order, which we then can transition into source order, and transitions are still transitions are still efficient because we continue to not use secure sort, and we continue to use the shuffle protocol. In the interest of time, gather was already in the original work, already decoupled into gather and an apply. So we continue to have this separation or distinction between gather and apply state. And we do something very similar that we did to propagate, wherein we come up with a new way of propagating, gathering information, just like propagate, which allows us to do this in a non-interactive manner. Which means now when we have multiple iterations, this allows us to have propagate can be achieved in just constant rounds, and apply E, all the interactive computations are pushed on to apply E. And the observation that we do, maybe I'll quickly talk about just the propagate. The simple observation that we do is that most graph algorithms require propagating information. The way you propagate information just requires you to, let's say, just send the message that's there at the vertex onto the edges. So what we do is we sort of do a prefix sum. We make the following observation. We say that what if, rather than just accounting for the edge, what if we account for all the information that is there prior to the current entry? So we essentially propagate information more than what is required. And so in order to correct whatever is the additional values that we have accounted for, what we do is we pre-process the list so that the additional information is can be removed when we perform the aggregation. Because we are doing this as a secure addition, it just depends on additions. This can be done non-interactively in MPC. And again, as I said, so you do the pre-processing in the vertex ordering, and then the transition to source order is still via shuffle, which can be done efficiently. And then again, you depend on linear operations to remove the additional information that you have gathered as a part of propagate. So it's a very similar idea that we do in gather as well. We essentially rely on just additions to ensure that the aggregated information is present at the vertices. Yeah, just to conclude, if you were to use adjacency matrix representation, you would still have order 1 rounds, but then you pay the price of order V square communication cost. The state of the art back then, which was Araki et al., would still require order n rounds and order n communication in the non-optimized variant that they had, whereas we showcased that we can bring down the rounds to just order 1 because everything boils down to non-interactively updating the entries, and the communication is also improved to just order n. And we've evaluated our protocols as well, and I'd like to point you to the paper for further details. And I'm open to questions, if any.
Questions? Okay, I do have a question. So in the comparison slide, you compared the number of rounds and the communication. Could you comment on how the local computation for your scheme for graffiti compares with the adjacency matrix and graph SC based schemes?
So computation wise, we don't really have, I mean, okay, we still do have some initialization cost because, okay, I didn't mention that, but as a part of initialization, we still have to rely on sorting, but we just do that once. But otherwise, the computations once your initialization phase is done, the message passing phase literally comes for free almost. So computationally, we are much better than the prior works.
And maybe just a quick follow-up question. I think you mentioned that both your work and the prior works were all in the semi-honest setting.
Yes.
What challenges would you foresee in maintaining, let's say, the same number of rounds or similar kind of communication if you were to consider malicious security?
I think you would, I think this would still extend to malicious, but then you would require some additional verification checks, which would cost a couple of more rounds, but I think it should be doable. I mean, it would be not, of course, not as efficient as this, but it would come at the cost of a couple of more rounds for verification is what I believe.
Okay, thank you. If there are no more questions, let's thank Varsha again for the very nice talk.
Thank you.
So the next talk is titled Round Efficient Three-Party MPC for Dynamic Data Structures. The talk will be given by Aditya Vadapalli. Aditya is an assistant professor at IIT Kanpur. Over to you, Aditya.
Okay, thank you. So I'm going to talk about two of our recent works. The first one is a new distributed ORAM protocol that appeared a year or 2 years back, and then is a follow-up work that we did, which uses the distributed ORAM protocol to build efficient dynamic data structures in MPC. The reason I'm going to talk about this work is that what I've realized when I started working on distributed ORAMs sometime in 2023, and I realized how powerful distributed ORAMs can be if you want to build data structures in an efficient manner which have several applications. Okay, so let's just begin to motivate what ORAMs are. So essentially you have Bob, who has terabytes of data. He doesn't have enough storage, so what does he do? He has a friend, Alice. He does not really trust Alice, but Alice has a lot of storage, so she basically has what he needs. And Bob basically encrypts his entire data and gives it to Alice, and whenever he wants to make a query, he picks it up from Alice's storage. This is great. Because it is all encrypted, so Alice really does not know what Bob is accessing, but it does leak something, right? Because outsourcees are not really trustworthy. So where is the problem? The problem lies in access patterns. Alice, who is handling this encrypted database, can learn the access patterns of Bob, which can leak sensitive information. Okay, so ORAMs are essentially algorithmic techniques, and what they do is that they provably encrypt the access patterns. What do I mean by provably encrypting? It basically means that any access pattern should look exactly the same to the adversary. It should be computationally indistinguishable. So, for instance, accesses to indices 1, 1, 1, 1, 1 or 1, 2, 3, 4, 5, 6 should look exactly the same to the adversary. Okay. So what really ORAMs do at the heart is that they take a logical access and they turn it into a bunch of physical accesses such that these physical accesses are computationally indistinguishable for all logical accesses that you do. So this is one family of ORAMs, and these are the ORAMs that were studied for a long time, and this is essentially called the client-server model, in which the ORAMs work. There has been recent work on distributed oblivious ORAMs, distributed oblivious RAMs, and here the setting is slightly different. Here there is no notion of a client or a server, and this is basically what my talk is going to be about. So we have, for example, in a two-party setting, we have the parties holding the shares of a database, D0, D1. They also hold shares of an index, I star 0, I star 1. They also hold some value, shares of a value M, M0, M1. At the end of the protocol, if they do a read operation, they are supposed to get shares of Z, Z0, Z1, such that they are shares of the I starth index of the database. That is, the shares of the index, the shares of the value at the index, whose shares they were holding. And if it was a write operation, quite naturally, they are supposed to get new database shares such that a write operation has happened at the I starth location with the value M whose shares they hold. Okay, so now that we understand the problem of distributed ORAMs, let's talk about a few of the distributed ORAMs that have been studied. They basically come in two main flavors as we see it. One are computationally efficient and other are communication efficient. So typically papers like Raman and three-party circuit ORAM. So Raman appeared in CCS 2023. The three-party circuit ORAM is a slightly older paper. So their computational cost is somewhere in polylog n. However, they have a relatively large round complexity. Then you have papers which are the so-called communication efficient distributed ORAMs, and papers like FlowRAM and the work that I'm going to present, DuoRAM, they fall under the category of communication efficient. So here, what they do is that you are actually going for the worst possible computation cost, which is linear. However, the gains that you get are extremely low round complexity and extremely low bandwidth consumption. Okay. So these works are essentially variants of tree-based and square root ORAMs. So these, if you're familiar with the ORAM literature, these were how the client-server ORAMs were built, and those variants are adapted in Raman and three-party circuit ORAM. The communication-efficient ORAMs typically are built using distributed point functions. Distributed point functions, like we have seen, I think yesterday as well, are succinct way to share one hot vectors among multiple parties in an efficient manner. Okay, so let's talk about a few of the works. So FlowRAM was the work which by Donner and Shelat. It's an asymptotically pessimal ORAM in the sense that it has linear computation cost. However, they optimize for round complexity and bandwidth consumption. So I'm going to talk about FlowRAM in one slide, and then I'm going to talk about our work and the improvements that we do. The main idea of FlowRAM is that they store the write-only memory and a read-only memory in a completely different ways. Write-only memory is stored in the most natural way that you would think. You have shares of the database, and that is essentially the write-only memory. The write operation also happens in a very natural manner. You have shares of a one-hot vector which come from a distributed point function, and these shares are added to their local database shares. So very simple of how write-only memory is handled. Read-only memory is different, but again, the two parties hold exactly the same contents. They hold encrypted databases, usually encrypted via a PRF, and they do a private information retrieval, again using distributed point functions on the write-only memory. On the read-only memory, and then you basically decrypt whatever you had retrieved using a private information retrieval protocol. Okay, so one natural thing is that what happens when you make a write into your write-only memory, the read-only memory now stops corresponding to what was actually written. So that's the reason they have something called a refresh operation, along with a stash. And what this allows them to do is to switch. It's a nice, efficient way to switch between a read-only memory and write-only memory. Yeah, so and this switch asymptotically takes around square root n communication. So the question that we asked, so this paper appeared in IISc 2023. The question that we asked is it possible to build a distributed ORAM such that you don't have to make this switch? And the answer to that is yes, we can do that. And the main idea is as follows. The main idea is that you keep the read-only, you keep the read memory also as secret shares of the database. And you would essentially want to compute this particular dot product in MPC. Now, yes, this is a very simple idea, but it has a major problem. And the problem is that the way every time you would want to do an MPC to compute this, you would have to spend linear communication to do that. So we have the first secret sauce in developing efficient reading in DuoRAM is our read protocol, and this protocol requires the following invariants to hold true. So party P0, it holds database, the share of the database, and something called D1 tilde, and D1 tilde is the blinded version of the data of the other party's database. The blinds are held by P0 and P1 as well. Along with that, they hold F0, G0, H0, F1, G1, H1, and these are all shares of the one hot vector. Along with that, you also need party P2, and party P2 holds these blinds, and they also hold H1 and G0, which are the shares of the one hot vector, but they hold very specific shares, is what they hold. And I'm not going to delve into the protocol, but what you have to believe me is that if these invariants hold true, and if these are indeed shares of a one hot vector, then you can have an MPC protocol. You can basically have an MPC protocol that allows you to do a read operation. Okay, that's great, but we will again be faced with the same problem that FlowRAM faced, and that problem is what happens when you do a write operation. When you do a write operation, you would do the write operation, like I said, in the most natural way. That is, you have shares of now a scaled one hot vector. It is scaled by m, the value that you want to write at the I starth index. You would add this. Now, what is the problem now? The invariants stop holding true, and your MPC protocol that we had will not work anymore, because for us, for the MPC protocol to work, we would want D1 tilde should be equal to, they should indeed be the blinds of the actual database, and because the database changed, these invariants have stopped holding true. Now, however, if you want to get the blinds in a naive way, this would be extremely inefficient. You would have to communicate the size of the database amount of data, and that is not what we would want. Okay, so the question is, can we get new blinds and blinded shares that satisfy these invariants without linear communication? And the answer to that is a yes, of course, and that is why this talk is there. So let us see how we do this. So you might have noticed that we had like 3 shares of those one hot vectors that we needed, and those will come into play in order for us to get the new blinded shares without linear communication. So this is the initial thing that we had. We had D0 plus R0 is equal to D0 tilde. So this is essentially what we had before we did a write operation. And then we do the write operation by doing this. This is party P0's view, and the invariant stops holding true. Now, what we would want to do is that we want to somehow fix this without doing much work. And the idea is that, if you notice, because F0 and F1 are shares of one hot vectors, D0 almost has the information to fix it. It nearly has it, but not quite. It's almost equal, but it is still not completely equal. So this is where the two other vectors will help us out, G0 and G1. And now if you notice that if G0 is subtracted from R0, and you add an additional G1 into D0 tilde, now this whole thing starts holding true. And now what you can see is that this whole quantity becomes your new D0 tilde. You have D0 prime, which is the new share of the database. And now you have the new blind, which is R0 plus G0. So just by having these additional one-hot vectors, we are able to satisfy the invariant again. And now since you satisfy the invariant again, the MPC protocol to run the read operation works very well. So what do we get out of this? We use distributed point functions to produce shares of the one-hot vectors. These DPFs have to be produced in MPC. We use the technique by Donner and Shellart from CCS 2016 to produce these DPFs. Furthermore, we push the DPF production to a pre-processing phase. That is, you can actually produce the DPFs before you actually know where to write and what to write. And later on, you can adjust them whenever you get, in the online phase, whenever you get the information about what you want to write. And the result is that we actually have just one round of communication in the online phase and log-in rounds of communication in the pre-processing phase. And these is binary search on secret shares. And naturally, this is the most natural place where you would find application of distributed ORAMs, because let us say that you have secret shares of a database and you want to do a binary search for some element. What would you do? You would go to the middle element. This is not an ORAM operation, but after you have done a secure comparison, you either move left or right, and now this starts becoming an ORAM operation, and you do another ORAM operation, and finally you get what you want. Now, and very naturally you can use any of these distributed ORAMs to do it, but the observation is that using a general distributed ORAM over the entire database is a complete overkill for binary search. And the reason it is an overkill is that, yeah, like I said, if you use do-ORAM, you would require login do-ORAM operations. This means 3 login DPFs. But now let us start looking for a few patterns. This is the first read operation that you would do irrespective of what you are searching for, because that is basically what the binary search asks you to do. The next read operation has to be either of these two guys. It is either in this half or that half. So here you really need not do a do-ORAM operation over the entire database, but you have very specific areas that you would want to look at. Next, you would do a do-ORAM operation. These are the only 4 locations where you could go to, and these are the only 8 locations where you could find the next element, that the next pointer the next pointer would go to. So what this results that you actually do not require this many DPFs. You don't require 3 login DPFs. Rather, what you can do is that you can use what are called incremental DPFs and just use 1 incremental DPF, and that would be completely enough to do a binary search. And incremental DPFs are essentially DPFs which have a final correction within each layer. So you can think about 1 incremental DPF as a DPF of size 2, size 4, and so on. So and that's basically the sizes that you need for each of these layers. So this is a non-do-ORAM operation, and this do-ORAM operation can be done by the first layer of the incremental DPF. This do-ORAM operation can be done by the second layer and the third layer, and so on. So I hope this gives you a nice flavor of how distributed ORAMs can be used to do some algorithms. Now, the last bit that I'm going to touch upon is how would you do, say, a heap data structure. So there are two main operations that we would look at: insert and extract min. So let us say you want to do an insert operation. Now, the main idea is that we will just use our binary search operation that we the binary search protocol that we did in the warm-up. And what we are going to do, what we know for sure is that when we insert a new element, it is going to lie on this path. We can do a binary search to find out exactly where it lies, and that's where it lies. Then we obliviously shift all of them over here. Now we obtain the index of where it needs to be written, where a hole has been created, and we basically insert the value in that hole. Very, very simple, and this is a very nice way to do an insert operation. Now extract min, which is slightly more interesting. So, and the main idea is that usually is pretty far away, and if you want to develop data structures using distributed ORAMs, it might be very useful to actually build data structure specific ORAMs, and yeah, we have a lot of works in the pipeline where we are doing this. Now I'm happy to take questions.
Thanks for the very nice talk. Questions?
Oh, nice talk, by the way. Do you support something like pointers? Like in regular programming, we have like a pointer, and that value itself is actually stored in the RAM, and whenever we dereference it, we can access some other memory location. Do we have something like this protocol for realizing this?
So I can't completely understand your question. So what is it that you want? You're asking for the support of? You're storing the index in the memory. Is that what you're saying, or?
Yeah, effectively.
Yeah, I think, yeah, you can do that. In fact, I mean, so you just, the value that you store over there would be an index, and yeah, I don't see a reason why it can't be done, but maybe I'm not understanding exactly what you're asking, but.
Because the access pattern itself might depend on the data which is being on the RAM, so maybe there are some circularity issues, or I don't know.
I don't think so. I don't think so.
Okay, there seems to be one more question.
Yeah, so, here.
Oh.
Okay. What do the hidden constants look like in the, like you have O of log and asymptotically, but what are the hidden constants?
No, there is no constant. It is just log n rounds.
So it's already practical then?
Yeah, it is actually pretty practical. It's actually very practical. Yeah. So I can't remember the numbers at the top of my head, but you can actually do ORAMs of the size of at least 2 to the 25 to the 26 within seconds.
Can we make use of RAM resistive random access memory so as to save this data structures as such?
I don't know. So what are RRAMs?
It's related to neuromorphic computing.
So I am not aware of that, so I can't answer that question.
Okay. Thanks for the nice talk. So I'm curious, so the I guess FlowRAM and related works are usually in the semi-honest model.
This is also in a semi-honest model, yes.
Even the 3PC?
Yes.
Is there any scope for maybe upgrading to malicious security in the honest majority setting or something like that in the 3PC?
Yeah, there is, but you would have to do it in the regular way of making sure that, just having another protocol which ensures that they all are behaving honestly. So the additional costs will be what you would expect them to be. So yeah, I think, so the efficiency would suffer quite a bit if in the malicious setting. That's what I think.
I see. Thanks.
Yeah.
Yeah, sorry, just a follow-up on the previous question.
Yeah.
Like, just having like a maliciously secure DPF scheme would directly give rise to a maliciously secure ORAM, or will there be additional challenges?
No, the read operation also needs to be maliciously secure, and then if you have the three-party read protocol that we have, that is also malicious secure and malicious DPFs, then that would be enough for malicious ORAMs.
Okay, thank you.
Yeah, maybe I had one final question. So you mentioned the use of incremental DPFs. These typically require public key operations. How does that?
No,
or
they
does it?
don't. They
Okay,
don't
they
require public key operations.
Okay.
So the incremental DPF essentially is just that you have a DPF tree, but so a typical DPF only has a final correction word at the last layer, which basically converts that random value into the value you're looking for. In incremental DPF, you have log and correction words for each layer. So essentially what you get are DPFs of size 2, 4, 8, 16, and so on. So there is no public key operation that's required.
Okay, okay, thanks. Okay, I think in the interest of time, we'll wrap this up. So let's thank both the speakers of this session once again for the wonderful talks. I believe we have a panel discussion now, so please stay around for that. Thank you.